In this tutorial, we're going to introduce you to material plasticity in Abaqus and show you how to set up a simulation to include it. In addition, we're going to perform a restart analysis so you can see how this is done in Abaqus. In a previous tutorial, we analyzed a planar shell or plate bending under the action of a load. The plate in that example was provided elastic material properties, and the load magnitude was such that the maximum stress on the plate was less than the yield stress of its steel material. Now we're going to modify that simulation to demonstrate plastic behavior. The planar shell will be loaded with two concentrated forces of 270,000 newtons each, so that the stress in some regions will exceed the yield stress of steel and the plate will deform plastically. The material used is a generic steel with a density of 7,872 kilograms per meter cubed, a Young's modulus of 200 gigapascals, and a Poisson's ratio of 0.3. The plasticity behavior of steel is represented by the stress versus plastic strain curve displayed here. The plasticity model in Abaqus defines the post-yield behavior for most metals. The data required is the true yield stress of the material as a function of true plastic strain. The first data point corresponds to the initial yield stress, also known as the elastic limit of the material. Hence, the plastic strain value associated with it should be 0. It is important to know that Abaqus expects the data to be supplied in the form of true yield stress and true plastic strain. This is the case in the current example, hence we can use this data to define the material plasticity behavior. In the course of this video, we will also discuss how to deal with material test data that is in the form of nominal stresses and strains, as is often the case. At the end of the load step, we will release the load, allowing the plate to spring back and recover its elastic deformation. The plastic deformation, of course, will not be recovered. However, we will not perform the springback step in the same analysis as the load step. Instead, we will perform the load analysis as a complete job, request Abaqus to output a restart file, and then use this restart file to continue the analysis as a new restart job from where the previous one left off. Restart analyses are useful because they allow you to add another analysis step to a completed analysis job. This is very handy if your analyses take several hours or days to run, and you don't wish to add the new step to the original model and rerun the entire thing from scratch. It also sometimes helps to run a multi-step simulation in the form of separate jobs with restarts, so you can examine the results of each analysis and confirm that it is performing as expected. Restart files are also useful if your analysis fails or crashes at a particular point. You can try readjusting your loads or constraints and continuing from a particular step or even a specific increment. However, you must request Abaqus to output restart data before running the original simulation, otherwise no restart file will be created. Let's start Abaqus and work through this. Instead of creating the model from scratch, we're going to start with the one created in the planar shell bending tutorial. Let's rename the model Plastic Plate Bending Model. We will modify the material AISI 1005 steel, created as part of the original model. Let's rename it Steel, since we will only use a generic yield stress versus plastic strain curve for steel. Change the Poisson's ratio to 0.3. Create a new plastic material behavior by opening the mechanical menu and choosing plastic from the plasticity menu item. Type in the yield stress versus plastic strain data for the material. As you fill out each cell, hit the Enter key on your keyboard to move to the other cell. It's possible you have your yield stress versus plastic strain data in an external file, and typing it out into this table is tedious. There's another way of getting this data into the table. Clear the contents of the table by right-clicking in any cell and choosing Clear Table. I have the tabulated values in a text file with a tab separating the stress from the strain, and each stress-strain pair on a new line. Right-click in any of the cells and choose Read from File. Click the Select button and navigate to your file. Notice that below the file name, Abaqus tells you that the fields can be delimited by spaces, tabs, or commas. In our case, we have tabs separating our stresses from strains, and Abaqus will be able to identify the two separate columns thanks to the tab delimiter. We tell Abaqus to start reading values from our text file into the first row and first column of the table. Click OK. Abaqus populates the table with the values from the file. If you want to visualize the yield stress versus plastic strain curve, you could plot it in a tool like Excel or MATLAB. But there's an even easier way to do it in Abaqus. Right-click anywhere in the table and choose Create XY Data. Set the name of the XY data to steel stress versus plastic strain. Since we want plastic strain on the x-axis and yield stress on the y-axis, we tell Abaqus to read the x values from column 2 and the y values from column 1. Click OK to close the Create XY Data dialog box, and click OK to close the Edit Material window. Abaqus informs you in the message area that the XY data has been created. Switch to the Visualization module. In the results tree, expand out the XY data container and double-click on steel stress versus plastic strain. You see the curve plotted in the viewport. We can modify the appearance of the curve to reveal the data points. Use the XY Curve Options tool. In the Curve Options dialog box, set the line style to dashed. Check the Show Symbol option to display the data points. We will change the symbol to a diamond shape and the size to large. Click Dismiss to close the dialog box. You now see the curve with our yield stress versus plastic strain data points. Notice that Abaqus has interpolated linearly between these points, hence you see straight lines connecting them. Abaqus Standard will use the user-supplied data where possible and the linearly interpolated values for all the intermediate points when running the simulation. It makes sense, therefore, that the more points you provide, the more accurate the representation of the material plasticity. Abaqus Explicit, on the other hand, will regularize the data for the sake of efficiency. In layman's terms, this means it will generate stress-strain data points that will form a nice smooth curve. However, it is possible that the points it generates may not coincide with the original user-supplied data points. Abaqus Explicit will attempt to generate a sufficient number of intervals so that the maximum error between the regularized and user-supplied data is less than 3%. Also note that Abaqus will not attempt to project your curve beyond the last point. The stress is assumed to be constant outside the range defined by the data supplied, hence the curve is perfectly horizontal after the last supplied data point. This means that the stresses in the material will not exceed the stress of the last stress-strain point on the curve, and once the stress in the material reaches this value, the material will deform continuously until the stress is reduced below this value. Hence, you must check to make sure that the stresses in your model never reach this portion of the curve, or your results will be meaningless. Material test data is often in the form of nominal stress and strain, and I want to take a moment to explain how you would convert the nominal stress-strain to true stress-strain data that Abaqus can use. You find the true stress from the nominal stress and nominal strain using equation 1. The true strain is found from the nominal strain using equation 2. Since the strains obtained from the test data are probably not plastic strains, but rather the total strain, this total true strain needs to be decomposed into its elastic and plastic components. The true elastic strain is obtained from the true stress and the Young's modulus using equation 3. The true plastic strain can then be found by subtracting the true elastic strain from the total true strain as shown in equation 4. Now let's change the initial increment. Abaqus standard solves a problem by applying a fraction of the load in an increment, solving the system of equations, and iterating till convergence, and then increasing the load in the next increment. This procedure is repeated till the final increment when 100% of the load is applied. Currently, our problem is set up so the entire load step occurs in one increment. However, in a nonlinear analysis, it is almost always better to set smaller increments. This is because the solver is unlikely to converge to the solution when it applies the entire load in one increment, and will internally do a cutback and try to solve with smaller increment size. For highly nonlinear problems, Abaqus standard might have to reduce the increment size repeatedly. This wastes computational time. Hence, it is preferable to have multiple increments from the beginning in any nonlinear problem. The way we can achieve this is by setting the initial increment to a fraction of 10%. So, if your step time period is 1, set the initial increment to 0.1. This means that the solver will apply 10% of the load in the first increment. Abaqus will automatically adjust the sizes of subsequent increments based on the convergence behavior of the solution, hence you only need to specify the initial increment. It is hard to determine exactly what will be a good initial increment, and Abaqus will in fact let you change even more options, such as limiting the minimum and maximum increment sizes, as well as the total number of increments. However, an initial increment of 10% is generally assumed to be a good starting point, unless you have already run the simulation previously and examined the status file. Double-click on the load step in the steps container to see the edit step window. You see that the step time period is set to 1. Switch to the incrementation tab. Here you see the initial increment size is also set to 1. Since the initial increment size is the same as the total time, Abaqus will attempt to solve the problem in one increment. We shall change this increment size to 0.1. Abaqus will now apply 10% of the load in the first increment. Note that time has no physical meaning in a static analysis. It is only meaningful when comparing it with the initial increment. So you could instead set the step time to 5 and the initial increment size to 0.5, and it would mean exactly the same thing as setting the step time to 1 and the initial increment size to 0.1. Now let's modify the loads. We will change the concentrated forces to 270,000 newtons in the negative y direction. The model is now almost complete. We will create a new job for this analysis. If you already have an existing job, you can delete that. We shall call our new job Plate Job Plastic and set it to solve the plastic plate bending model. The job type is set to full analysis. Run the job by right-clicking on it and choosing Submit. Abaqus warns you that history outputs have not been requested. Click Yes to continue. You see that the job has been aborted, and Abaqus tells you about errors in the message area. The important one among these is that Abaqus was unable to find the material AISI 1005 steel. Since we modified this material and changed its name to just steel, it is apparent that some part of our model is still referring to the original material and has not been updated. It is likely the section property. Right-click on Plate Section in the Sections container and choose Edit. Abaqus informs you that this section refers to the material AISI 1005 steel, which no longer exists. Since the new material steel is the only material in our model, It is now the only one displayed in the drop-down menu. Click OK. Let's try to run the job again. This time it goes through till completion. Let's view the results. Plot a contour on the plate. The mice's stress is displayed by default in the legend. The text of the legend appears quite small on my system, so I'm going to increase the font size to make it more readable. In the viewport menu, click on Viewport Annotation Options. You get the Viewport Annotations Options dialog box. Switch to the Legend tab. Click on Set Font. We will leave the font set to Verdana and change the size to 14. Notice the legend is checked in the Apply To section. This means our change to the font size will apply to the legend only. We could in fact set the font of the title and state blocks from here too, but we'll do that from the Title Block tab instead. Switch to the Title Block tab and click Set Font. This time we will change the font of the title block and the state block. Set the size to 14 and change the font to Times New Roman. Also check Italic. You see the changes to the font in the viewport. Now let's talk about restart analyses. As mentioned in the overview, a restart analysis allows the user to continue an analysis from where it stopped. The analysis may have stopped because it was unable to converge, or the maximum number of increments for the step was reached, or the computer may have run out of disk space or crashed. It's also possible that the analyst intentionally wished to separate the steps of the analysis into separate jobs so that the results of each step can be viewed and the validity of the solution till that point can be confirmed. In all of these cases, a restart analysis will allow the solution to continue from where it left off. It is also useful for transferring results between Abaqus Standard and Abaqus Explicit. Let's take a look at the files generated by Abaqus during the analysis. These will be in your Abaqus work directory, which by default is in the temp folder in the C drive. In my case, I have it set to a folder called Abaqus temp in the C drive. You see a number of files here, and you have likely noticed these being generated every time you run an analysis job in Abaqus. The file we are looking for is a restart file with a .res extension. This is a file that can be used to continue an analysis. However, no restart file is present. This is because Abaqus Standard does not generate a restart file by default. It needs to be specifically requested. So let's return to Abaqus and request restart output. Switch to the step module. From the output menu, choose Restart Requests. You see the Edit Restart Request dialog box. It has a table listing the steps of the analysis, the frequency and intervals at which restart data should be written, and options for overlay and time marks. Restart output is written for the steps requested, not the entire analysis. The analyst has two options for specifying how often restart data should be written. If a frequency n is specified, then Abaqus will write the results after each increment whose increment number is a multiple of n. So the restart data is written every nth increment. In addition, the restart data will be written at the end of the step. If an interval m is specified, then Abaqus Standard will divide the step into m time intervals and write the requests at the end of each interval. When specifying an interval, the checkbox for time marks will become available. If the analyst checks time marks, the results will be written at those exact time intervals, whereas if time marks is left unchecked, the results data will be written at the increment ending immediately after each time interval. The frequency option is available only in Abaqus Standard, whereas interval is available in both standard and explicit. Change the frequency to 1. This tells Abaqus to write the restart data at the end of every increment. The checkbox for overlay becomes active. This option allows you to tell Abaqus whether the restart data written at the required increments should be appended to the restart data written at previous increments. We are going to check overlay, so every time Abaqus writes restart data, it will replace the previous data. So even though we are writing restart data at every increment thanks to our frequency of 1, we only hold on to the latest set of restart data. As mentioned before, Abaqus will write restart data one last time at the end of the analysis step. Since we are overwriting previous restart data, we are basically saving the restart data at the end of the load step. The overlay option is useful because the analyst cannot specify what data is written for the restart. Abaqus writes a complete set of data each time, so it is possible for your restart file to get quite large. Saving only the last set of data alleviates this issue. You might ask why we are writing the restart data at every interval anyway, if all we need is the one at the end of the step. The answer to that question is that quite often restart data is written so an analysis can be restarted after an error or crash terminates the simulation. It is not known at that point what increment this error will occur at, hence you specify a frequency or time interval of sufficiently small size that your restart point is quite close to the point the simulation terminated. Of course, writing restart data to a file itself takes time, so in a large simulation you should avoid writing restart data at every increment as we have done here, and should instead pick a lower frequency. Now that restart data has been requested, let's run the analysis again. Once the analysis is complete, check the work directory. This time you see a restart file, plate.plastic.res. Now we shall set up the restart analysis itself. When performing a restart analysis, the model must be the same as the one used in the original analysis up until the restart location. This means that any geometry, materials, steps, loads, boundary conditions, fields, interactions, and meshes defined in the original model must not be modified. New sets and amplitude curves may be defined in the restart analysis model. New steps may be added, as well as new loads and boundary conditions, which become active after the point of the restart. The original loads and boundary conditions must be active up until the restart. However, they may be deactivated for steps that occur after the restart, as will be done in this example. The easiest way to replicate the model prior to the restart is to copy it. Right-click on Plate Plastic Bending Model and choose Copy Model. We shall name it Plate Springback Model. The new model is added to the model database. Right-click on it and choose Edit Model Attributes. In the Edit Model Attributes window, focus your attention on the Restart tab. This is where we specify the settings for the restart analysis. Check Read Data from Job. Abaqus expects you to type in the name of the job exactly as it was spelled in the original model. This, by the way, is the same as the name of the output database file from that job without the .odb extension. Our job was named Plate Job Plastic, hence type it in exactly as that. Abaqus gives you a few different options for which point to restart from. You can restart from the end of the step. This is what we will be doing. In fact, since we chose to overwrite restart data from previous increments, and our simulation ran through till the end of the loading step, the only data we have is that at the end of the step. However, you have the option to restart from an increment if you have the required data. In such case, you would have the option to terminate the original step at that increment and begin the newly defined step, or allow Abaqus to complete that step from the restart point using new loads and boundary conditions before moving on to the new step. Since we need to type the name of the step exactly as it appears in the original model, we can look it up in the model tree. Now we create our new step, spring back. It too is a static general step. Once again we set the time period to 1 and the initial increment size to 0.1. We need to remove the load from the plate so that it can spring back and recover its elastic deformation. Right-click on Loads in the model tree and choose Manager to view the Load Manager. Notice that the concentrated force loads have been propagated to the springback step in this restart model, just as they would by default in a regular model. Click on Propagated and click the Deactivate button. The load is no longer active during the springback step. Click Dismiss to close the Loads Manager. The model is now ready. The final task is to create the job. Let's call it Plate Springback Job and apply it to the Plate Springback model. In the Edit Job window, notice that the job type has been set to Restart by default, since we added the restart settings to the model attributes. Run the job. Let's view the results. Display the Mises stresses on this plate. In a restart analysis, the first frame of the restart is the same as the last frame of the original model. To verify this fact, let's display both of these side by side. In the Viewport menu, click Create to create a new viewport. The viewport is not immediately visible because our current viewport is maximized to fill the available screen real estate. We can display it next to the current viewport using Tile vertically from the Viewport menu. Now you see the two viewports. The new viewport displays the same contents as the old one by default. Click on the title bar of Viewport 1 to make it the active viewport. Then double-click on Output Databases in the results tree. In the Output Database window, navigate to the output database of our original analysis, platejobplastic.odb. Viewport 1 now displays the results of this analysis. A quick way to check to see which output database is displayed, or to change it, is to use the ODB drop-down menu for the visualization module. Note that the ODB file name is also visible in the title block in the viewport. Display the Mises stresses on this plate. Click on the title bar of Viewport 2 to make it the active viewport, and ensure that the ODB displayed is platespringbackjob.odb. Once again, switch back to viewport 1. Now click the Frame Selector tool. The Frame Selector tool allows you to very quickly display the frame you desire using a slider. Since viewport 1 is the active viewport, the tool applies to this viewport. We display the last frame of the load step, which happens to be frame 14. Switch to viewport 2 by clicking on its title bar. Once again, click the Frame Selector tool. This time the tool applies to viewport 2, since that is the active viewport. We set it to display the first frame, frame 0, of the springback step. Compare the Mises stress contours and their legends in the two viewports. It is evident that the last frame of the original analysis has the exact same stresses as the first frame of the restart analysis. The state block in the viewport also verifies that we are looking at the last frame of load step and the first frame of springback. Switch to viewport 1. Change the primary variable on the contour to UT, which is translations and rotations, using the field output toolbar. Display U3, which is the displacement in the z direction, which is the direction perpendicular to the planar surface of the plate. Repeat the procedure for viewport 2. Notice that the displacements are also identical for the last frame of the original analysis and the first frame of the restart analysis. This should convince you that the last frame of the original analysis before the restart point is used as the first frame of the restart analysis, whether this is the end of a step or some increment we tell Abaqus to continue from. In this case, we told Abaqus to use the last frame of the load step as the restart point, hence the first frame of the restart analysis corresponds to it. It might be of some importance for you to note that the output database of the restart analysis only contains information pertaining to this analysis, and does not contain the information from the original analysis. So when viewing the ODB for the restart analysis, the first frame we see is the first frame of the restart, or the last frame of the original analysis. It is not possible to view frames and field or history outputs for steps that occurred in the original analysis, and you will need to open that ODB file separately in the viewer, as we have done here. As a final note, it is possible to render the plate profile in the same manner that you rendered the beam profiles in the beam frame tutorial. In the viewport module, choose the View menu to open the ODB Display Options dialog box. In the General tab, under Idealizations, you have options to render beam profiles and shell thicknesses. Check Shell Thickness and click Apply. You will see the shell thickness rendered in the viewport. Note that it was also possible to render the shell thickness before running the simulation. For example, if you are in the Part module, you can go to Part Display Options in the View menu, and if you are in the Assembly module, you can go to Assembly Display Options in the View menu.